Okay, I guess we can start. Wow. So, okay, thanks for coming, everyone, for this first installment of the learning seminar. So, and this is supposed to be a learning seminar, so I'll hopefully bore all the experts completely. I do not intend to assume any background. So if I accidentally assume something, feel free to interrupt me. I mean, the goal is not to kind of, get over some such material, just to introduce you to a different topic every time. So I will be doing o-minimality. So yeah, I mean, feel free to interrupt. Okay, so this time I'll be talking about the o-minimal structures. So just by show of hand, how many of you are familiar with o-minimal structures? Okay, so yeah, to some extent, okay, half and half. So good. So I mean, so I will, as I said, I will not assume anything. Now, when talking about o-minimal structures, there's kind of a few different ways of introducing them. I'm going to follow the way that maybe the logicians would normally do it. And the reason is that this is how most of the papers in the area are written. Okay, so if any of you have been to Benny Zach's talk, there's kind of a different axiomatic way you can introduce things that doesn't talk about formulas or logic at all. If you actually read papers, then usually it is written in this logic language. So let me use the common language. So I'll start by fixing a collection of functions. So these will be functions from R n alpha to R. So could be a different dimension for every function. And I'll fix some collection of sets. Okay, so I'll denote them by R beta. Yeah. In R to the n beta. Okay, so for the logicians, these I would call the function symbols in my language, and these I would call the relation symbols in my language. Okay, that's why I use R here. And now I'll be thinking about formulas that you can write in first order logic using these functions and these relations. Okay, and I'll say that, okay, kind of the structure, this, structure in the o-minimal structure. So how do I want to put it? So the collection S of all sets can be written using this F alpha R beta with first order logic. First order logic is called the definable set, the definable sets generated by F alpha and alpha. And so if you don't remember or have never seen what it means, a formula in first order logic, I don't want to really define it. It's just boring, but I mean, I'll give an example and I think you can kind of understand what I mean. So I mean sets that you could write like, let's say I write something like, I want X and Y such that, there exists a Z, so that for every W, F of X and Z is equal to G of W and H of Y, something like that. And so I mean, you can write quantifiers, you can compose functions, where I wrote equals here, this would be one of my relations. Okay, so when I write this is equal to this, it's kind of, I'm saying that, okay, this pair F and G belong to the graph of equality. Okay, so I mean, I think it's easy enough to understand what I mean by general first order formulas like this. And oh, I did forget one little detail here that I wanted to add. So I'll add here, they're generated by F alpha, R beta, and constants. And constants. So by constants, I mean I'm going to allow in my formula to plug in any real number. Okay, and I didn't have to do this. So usually, if you're working in model theory, then definable sets would not include the constants, and you could say definable with parameters, and then you would allow any constant. Okay, but I mean, for me, this distinction wouldn't really be important, so I always throw in all the constants. Now, another thing to note, especially if you're reading kind of papers in hardcore, written by hardcore like model theory or minimalists, is that usually when model theorists talk about it, they don't necessarily consider things defined over R. Okay, so they will, I mean, the structure can be defined over anything. And usually when we talk about minimal structures, we are thinking about a real field. I mean, I will get there soon, but if it's done in logic, then it's not necessarily this real field, it's any model of the axioms of a real field. Okay, so you have kind of a first order axioms for what a real field is, and then you could take any model, and instead of R, you could take, for instance, a much larger field that's some kind of non-standard extension of the real numbers, where you have numbers that are smaller than any 1 over n, that kind of thing. So it's just something to keep in mind when you're reading these texts, because it can be quite confusing. So just keep it in mind. I'll always be sticking with things that are defined over R. And the kind of stuff that I'll be talking about, it doesn't really make a big difference, but sometimes it is important. Okay, so this is just a structure. It's not o-minimality. This is just what structure means in general. Okay, now I'll only be thinking about structures over the real field. So over the real field, that's how it's usually pronounced by logicians. And what that means is two things. Well, one is, as I said, I'm only going to restrict to the actual real numbers. Okay? I will not be taking some non-standard extensions or something like that. And the other thing is that it's not just over R as a set, it's over the real field. So I mean, I'm always going to be putting, so I'll always include the field operations plus and times in my F alpha, in these F alphas, and I'll include equality and inequality in my R betas. Okay, so whenever I'm writing these formulas, I'm always going to allow myself to use addition multiplication, and I'll always allow myself to use equality. I mean, equality is normally always included in any structure, but I'm thinking about the real field as an ordered field, so I'm also including this standard order relation as something I'm always allowed to put in my formulas. Okay, and from now on, whenever I talk about structure, it will always be over the real field in this sense. If I forget to, I don't know, say that I include one of these, then they're always included. Okay, so this is a structure over the real field. It's not o-minimal yet. The talk is about o-minimal structure. So o-minimal is an extremely simple definition once you have this set up. So let me just give the definition. So definition. So the structure S is o-minimal if every definable subset of the real line. Okay, so generally I can define subsets of any number of variables, right? I can write formulas in several variables and I'll get a subset of Rn. But now I'm talking only about definable subsets of the real line, and every definable subset should be a union, finite union of points and intervals. Okay, so it's only a condition about things that I can define in one variable, and it should be a finite collection of points and intervals. Another way of saying the same thing is that every definable subset has finitely many connected components. If you think about R, if you have finitely many connected components, it really has to be a finite union of points and intervals. Now, why is this called o-minimal? Because this is kind of the minimal thing you can get as soon as you include the order. Okay, because I put the order relation into my language, then certainly I can define intervals, and then using logical, the OR connective, I can define any union of intervals or points. So you cannot have less than this. So it is kind of minimal in this sense, that as soon as you put the order, you cannot hope to get less than this. Okay, so all the o-minimal structures are kind of agreeing on the level of subsets of R. Whenever you have an o-minimal structure, it will define exactly the union of points and intervals. Every union of points and intervals is definable, and only the unions of points and intervals are definable. But once you go to higher dimension, I mean, things can become very different. I mean, this only works kind of for subsets of the real line. And the kind of the idea behind this definition is that once we impose this, it should already force all the sets in every dimension to be very well behaved. This is kind of the magic of this definition. You define something only about subsets of the real line, but it will somehow, by kind of using the fact that we can cook up things using complicated logical formulas, it will allow us to prove that every subset of every Rn is quite nice. That's kind of the motivation for this definition. Okay, so before starting to give some theorems about o-minimal structures, I want to give some examples.
Sorry, can you say something about the terminology? Why do you call it o-minimal rather than something else?
So O is like for the order, and it is the minimal thing that you can get once you throw in the order as part of your language. Yeah, so I mean, for example, if you didn't throw in the order, if you just said, I'm going to, let's not throw in the order. So what are the things that I can obviously define? It would be only either unions of points or the complement of unions of points. And let's say you only put in equality. You don't put in the inequality. So you can write things like x should be equal to 1, 2, or 3, or you can write things like x should be not equal to 1, 2, or 3. And then you get another notion which is called strongly minimal. Okay, so it's kind of, for any kind of basic thing you throw in the language, you can define what is minimal for this choice. Okay, so what is the first example, the smallest example? It's what is called R-alg. So this is an example of an o-minimal structure, R-alg. So this is the smallest one. So what do I mean by the smallest? When I define an o-minimal structure, I said it has to contain, these, field operations and equality and inequality. So certainly anything that you define using these would be in any o-minimal structure over the real field. Okay, so the smallest one would be where I don't put in anything else. Okay, so R-alg is just whatever you can define only using field operations plus order. So these are actually called semi-algebraic sets in more classical terminology.
You can define the order with field operations, right?
What?
Can't you define the order with squares or something?
Yeah, in fact, you can define the order with square if you want to allow quantifiers. But now I'm going to, if you are allowed to project, then you can define the order after projection. But now I'm going to give a theorem that goes the other way, where I want to say you don't have to use projection. And if you don't want to use projection, then you should allow the order. Let me make the theorem and then maybe it will be clear. Is it clear? Well, let me state the theorem. So first of all, I want to say that just even this, it's not obvious that it's o-minimal from the outset. I mean, if you just had things that are defined using maybe equalities, then it would be quite clear that you have finitely many points or finitely many connected components. Maybe even if you allow inequalities, it's quite clear. But if you write a long, complicated logical formula with, exists and for all and complements, then it's already not completely clear. I mean, it's hard to imagine that you could create some, infinite collection of points like this just using algebraic operations, but it's not obvious. And this was studied by Tarski, and there's a famous theorem called Tarski-Zeidenberg theorem by Tarski and Zeidenberg. I mean, I guess it's independently, which states that, let me see how I want to put it. So every definable set here, every definable set in our algebra can be written using a quantifier-free formula. Quantifier-free. Okay, so what it means is that here, when I talked about the definable sets, and I said you could take any first-order formula. In fact, you don't even need these first-order formulas. You can use just equalities and inequalities, and you don't need to allow quantifiers like for every or exist. Okay, so this is kind of a non-trivial theorem. It's a theorem about, real algebraic sets. And what it basically boils down to is showing that if you have a set that's defined without using, so let's say I have a quantifier-free set, so I just write a collection of equalities and inequalities, and I project it, then it's again going to be quantifier-free. There is a way to take the formula where you projected one variable and rewriting it without using any projections. If you can show that, then this theorem will follow. Because basically you can take your formula and, every existential quantifier you can get rid of, and every universal quantifier you can just rewrite it like not exist not. So you can kind of inductively simplify your formula by removing one quantifier at a time. Okay, so this is the theorem. And what this theorem basically means is that, we don't really need this kind of more complicated notion of definable sets. It's much closer to what we are used to in maybe algebraic geometry. Okay, we still allow inequalities, but we don't need these formulas. Basically everything is a collection of equalities and inequalities. And it's maybe much more familiar for people in algebra. Okay, so if things always worked out like this, then maybe you wouldn't really need this kind of logical framework for dealing with o-minimality. It's kind of, the interesting logic happens when you allow quantifiers. If you can get rid of the quantifiers, then maybe you don't need so much logic to study these things. So it's just kind of a hint that things don't always work out nicely like this. Okay, so when this happens, this is called quantifier elimination. Okay, so here we can basically eliminate quantifiers from our formulas. All right, and the corollary of this theorem is that our algebra is o-minimal. Okay, because now if we have a definable subset of the real line, the theorem says, well, we can write it just using equalities and inequalities, basically about polynomials in one variable. Okay, so now you should just take a set that's defined by a bunch of equalities and inequalities with a polynomials in one variable, and then it's quite easy to see that this can only be a finite union of points and intervals. If you set some polynomial equal to 0, then it's already finitely many points. And if you only have some inequalities involving a polynomial, then clearly you have only finitely many points where these polynomials change sign, and so you'll eventually get some finite collection of intervals between these points. Okay, so this is a rather easy way of showing that something is o-minimal. If it has quantifier elimination, it basically becomes a question about functions of one variable, and then, okay, if it's some reasonable class, then you can probably see that it's o-minimal. Okay, so let me give kind of the next standard example where things already don't work out quite as nicely as this. So the next example I want to talk about is Rn. So in Rn, this little n here stands for analytic. This is called the analytic structure. So I'm basically going to start with the field operations. So field operations, and then that I always put in, and then I'll add all the analytic functions restricted to a cube. Okay, so I'll add every real analytic let's say f alpha from 0, 1 and alpha to r with the real analytic. So I'll say what I mean by real analytic. By real analytic on this kind of compact domain, I mean there is an open neighborhood where it's real analytic, or you can just say it's real analytic at every point of this compact set. So actually, for every point, there should be an open neighborhood where it converges.
Sorry, is the Tarski-Seidenberg theorem, is that an analog of the fact that every image of a variety is constructible?
It is kind of, yeah, it's a similar
proof, or it's very different?
I mean, the proof is quite different, I would say, because I mean, you have to use the order here somehow, right? And yeah, I mean, this Chevalier theorem, it's, yeah, but intuitively, I mean, it's the same kind of statement, just for a different language. Here, it's a language with an order. Yeah, but thank you. It's a good comment. So, yeah, so here I'm just throwing in any analytic function on the cube. And so this is quite useful. So it has a lot of functions, a lot more than the algebraic structure. And it's again o-minimal, but it's o-minimal for a different reason. So the first thing to note about this guy is that it doesn't have quantifier elimination. So Rn does not have quantifier elimination. And a nice example for this is a set as follows. Let's say I take x, y, and z such that z is equal to sine of x over y, and let's say x is smaller than y. Okay, so I'm going to take a graph like this. So because I mean, I can write x absolute value less than y absolute value, I can write this using the order. And then once I know that x is less than y, then x divided by y is going to live in some compact interval, -1, 1. And therefore, I can actually apply the sine function to it. So, I mean, I should, when I want things to be definable here, I should make sure that whenever I take one of my analytic functions, I'm really plugging in only values in some domain where it's analytic. I can't plug in values near infinity because sine is not analytic at infinity. Okay, formally I said that the functions are in 0, 1, and here I'm taking sine between -1 and 1, but I mean, trust me that it doesn't really matter. So this, you can quite easily see that you can write this, but there would be some elimination of quantifiers involved. I mean, there would be a quantifier involved if I wanted to write this, because I'm not really allowed to write x over y. Okay, that's not one of the operations in my language. So what I can write is I'll add another variable w. I'll say, you know, w is going to be equal to, well, I'll say that wy is equal to x, right? So that w will work out to be x over y. And then I'll say that z is equal to sine of w. And then I'll say there exists w. Right, and then this will be equivalent. Well, okay, and I'll still have these, but these are all. So I can kind of express this x over y by adding a variable and saying that, okay, there should exist some w, and then kind of projecting and forgetting about W.
Why don't you want to add, I mean, it looks to me fairly harmless to add dividing into your definition of what.
Well, I mean, it is harmless, but if you want to say, I mean, it depends on what do you want to differentiate. If you want to differentiate between structures that have quantifier elimination or don't have quantifier elimination, then it really depends on which language you selected. If you allow this division, then Rn does have quantifier elimination. Okay, so it's a theorem of Denef and Van den Dries, I guess. So Rn in the language that I defined here, it does not have quantifier elimination, but if you allow this division into your language, then it will have quantifier elimination. But on the other hand, then kind of the functions that you can write in your language become much more complicated. Because you have to think that once I added an operation to my language, I can kind of recursively apply it. I can write things like sine of, I don't know, e to the x divided by, I mean, I can kind of compose these various chains of analytic functions and divisions. And then understanding what a single function in your language means becomes much more complicated. It can have a complicated domain of definition and so on. So instead you can say, I'll use only these very nice functions. They have a nice domain of definition, but I pay by not having quantifier elimination. Okay, so yes. Anyway, so this you can try to check that it's actually not going to be definable by a quantifier-free formula. I mean, if you look at this surface in R3, it is not going to be definable using just this language that I gave here. The idea is you can kind of analytically continue. So if you had a function that locally vanishes on this graph, then, I mean, you can see that it will actually have to vanish on all these, it will have to vanish on all of these lines where x over y is given by any multiple of pi. And then if it has to vanish on all these lines, then, there's some accumulation point for the zeros and the function has to be identically zero. So really no analytic function can vanish on this thing. And then it's clear that you cannot write this thing using only equalities and inequalities on analytic functions. Okay, so this means that a simple kind of approach like Zeidenberg wouldn't work. And this makes proving o-minimality much more challenging. Okay, because to prove o-minimality, we have to understand all the definable structures and then all the definable sets, and then give some finiteness property. And if the definable sets are, you kind of express them in more and more complicated logical formulas, it becomes more and more hard to show something about all the definable sets.
But the two versions where you allow division or don't allow division, they define the same sets.
Yes, I mean, if you're only thinking about what is defined with quantifiers, then yeah, it defines the same set exactly because of this trick. Like whenever you want to add division, you can just encode it by adding another variable.
Showing that it is o-minimal to include division through quantifier elimination.
I mean, if you know, if you know that you have quantifier elimination after adding division, then yeah, you could do it like that. But historically, that's not how people went about it. So actually, I think it was kind of a conjecture by Lojasevic that he didn't say that it's o-minimal. The language of o-minimality did not exist then. But Lojasevic did have a conjecture for how we should understand all the definable sets in this language. And the conjecture was, well, he understood, of course, that it doesn't have quantifier elimination. You have sets that you cannot define using just quantifier-free things. But what he thought was that you can define everything using just projections. Okay, so let me just state the theorem. So it was kind of a conjecture, but it was proven by Gabrielov. And the theorem that every definable set in Rn is given by existential formulas. So it means a formula like there exists some y such that phi xy. Okay, so this is a condition on x, and phi is quantifier free. Okay, so it's not quite as strong as quantifier elimination. Quantifier elimination would say we are always given by formulas without any quantifiers. And here we're saying, okay, we have to go one step further. We have to allow a single existential quantifier, but that's it. Then we will already get everything. You don't get more by allowing more complicated formulas. And it's okay, this is maybe a logician's formulation. This is, by the way, called in logic, this is called model complete. So Rn is model complete. More formally with this language. So model complete means exactly this. Every formula is equivalent to an existential formula if you ever read some paper that uses it. But an equivalent formulation is that the complement of an existential formula is again existential. Okay, so whenever you have an existential formula and you write its complement, you can again express it using an existential formula. So once you can show this, then again, if you have any formula that has more complicated, I mean, in every formula you can replace every universal quantifier by just complement, existence, and complement again. It's the Morgan's law or something. And then you can kind of, whenever you have a complement before an existential quantifier, you can get rid of it by this theorem, and then eventually you'll end up with just existential formulas. Okay, so this is maybe the more classical formulation, and this is why this is called Gabrielov's theorem of the complement. Theorem of the complement. And the idea is that for o-minimality, this is nearly as good, okay? Because, okay, before we said that in the quantifier-free case, all the definable sets are just given using quantifier-free formulas, and we can use that to deduce o-minimality. Now we know that every subset of R is given by a projection of a quantifier-free set. So still, if we know that every quantifier-free set has finitely many connected components, then certainly also the projection will have finitely many connected components, and then we can deduce o-minimality. Okay, so I mean, once you know this, it again reduces you basically only to understanding the structure of quantifier-free sets. Okay, if you know that every quantifier-free set has finitely many connected components, then the projection of every quantifier-free set still has finitely many connected components, and then you know that your structure is o-minimal. Okay, so it's kind of a corollary that Rn is o-minimal. It's not completely trivial. You have to understand that if you have a set given using analytic equations, then it can only have finitely many connected components. That's something that has to be done, but this was already done by Loyasevich. Okay, so this is maybe the classical part of o-minimality. I mean, people did this, including this Gabrielov theorem, before o-minimality was invented. And I mean, you don't really need this o-minimal machinery to understand any of this. And the proof is completely, it's kind of a geometric proof that Gabrielov gave. So I guess the first case where a new structure was constructed beyond this standard analytic thing is the work of Wilkie on the exponential. Okay, so this is maybe my third example, Rx. So this is just given by field operations plus e to the x, which I think about as a function from R to R. Okay, so this is a structure which is, well, at least it's not obviously here, because here I'm only including analytic functions restricted to compact domains. Okay, and here I'm putting just e to the x on all of R. So this function is not restricted analytic, you could maybe imagine that you can define it using analytic functions and some formulas, but in fact you cannot. Okay, so this is actually a different structure. It's not contained in Rn, and Rn does not contain it. It's a completely different structure. And what Wilkie showed is that Rx is model complete. Okay, so that means, as before, if you take an existing, it doesn't have quantifier elimination. In fact, you can kind of write a similar example to the one I wrote with sign over there with using just, I mean, if I wrote z is e to the x over y, this would also work. And this would be an example in Rx. So it doesn't have quantifier elimination, but it is model complete. Okay, so whenever you have an existential formula and you take a complement, you can again write an existential formula for it. It's already quite a mysterious statement. It's not constructive. It's not clear where do you get this new existential formula from. And the proof of this theorem is already quite heavily model theoretic, at least the Wilkie's original proof. There are now other modern proofs, but I mean, the original proof was quite model theoretic for this. And again, a corollary using also work of Khovansky, maybe I'll talk about next time, is that Rx is o-minimal. And so again, because we know it's model complete, showing it's o-minimal basically means we should consider now systems of equations that are now involving e to the x, so polynomials and e to the x. And we want to know that the number of connected components for every collection of equations like this is finite. Okay, because, yeah.
So when you're using this theory, like when you already know that something is o-minimal, is important to distinguish between things that are given by quantifier-free formulas and things that are not, or is that something that primarily comes in checking that?
It is, I mean, sometimes it's important, sometimes, I mean, if you're using o-minimality at the kind of the most basic level, then, you know, once you know something is o-minimal, there are a bunch of theorems that are true for every o-minimal structure, and then it's not important. But sometimes if you want to deduce more, you want to understand something about the structure of the definable sets in your structure, then knowing that it's, let's say, model complete, it gives you some information about the structure. So if you're trying to deduce some like finer properties of things in your definable, I mean, of definable sets, then this can be useful. But yeah, I mean, you know, in the end, you know, there's an axiomatic definition of o-minimal structure. There are a lot of theorems that are just true for every o-minimal structure, and then you don't really need to know about the model completeness. Okay, but I did want to explain that, okay, how do you get o-minimality? Let's say for Rx, you say because of the model completeness, it's enough now to just look at quantifier-free kind of systems of equations and say that there's finitely many connected components. Okay, and in the case of Rx, it was already known by Khovansky that there's this kind of finiteness. Whenever you write a system of equalities and inequalities using polynomials and x, you will have finitely many connected components for the solution. So this is, it's called the theory of Pfaffian functions, or Khovansky's pheunomial theory. So somehow usually the gap between going from this kind of more like algebraic geometry type of questions, where it's just equations and inequalities, and going to an o-minimal theory kind of questions, there's this gap from from just things that are defined using equations to things that are defined using formulas. And to bridge this gap, you need something like model completeness or quantifier elimination or some other. I mean, in some cases, it's neither, it doesn't have quantifier elimination and it's not model complete, and one can still deduce o-minimality in an even more complicated way, but I just wanted to give some examples or how it works in the standard settings. Okay, so this is, yeah.
A very basic question. So I know how to prove that X is not contained in Rn, but already assuming cell decomposition and so on. Because then it's polynomially bounded for R and it's not X is not there. Is there a simpler proof then?
A simple proof without using polynomial boundedness. Yes. I'm not sure. I'm not sure. In fact, I mean, it is maybe an older theorem, I think already by Rosevich, that if you have a definable curve in Rn, it's actually an analytic curve. Okay, so I mean, you can do, that's not, it doesn't require all this machinery. I mean, you can, just for curves, you can prove that you don't gain more when you project. Okay, so in fact, you only need to show that the graph of e to the x is not an analytic curve at the around infinity, and that is quite obvious. So I mean, I think this was definitely known to Rosevich before Gabrielov even proved his theorem. But still, you have to do something. So yeah, if you ask me how to prove it, I would say use polynomial boundedness. In fact, I mean, I might get to polynomial boundedness by the end of the talk. Okay, so I mean, we introduced Rn, Rx, and now the final one I want to introduce is R, where you throw in both N and X. Okay, so this is kind of, you know, we're just going to take everything in Rn and add everything in Rx. And that's the structure Rnx. Yeah.
Going back to Rx, you said the proof was very model theoretic. Can you just give an idea of what that means? Like what?
So, I mean, what Wilke does is he passes from R to a much larger structure where, you know, he adds a lot of non-standard numbers, and then he shows that there you can solve every system of equations in a certain sense. So, but you have to kind of work with these saturated models that are much bigger, and it's kind of like non-standard analysis if you're familiar with it. In all cases that I know, it's not really necessary. It's kind of a way of encoding the proof in a nice way, as it often happens with non-standard analysis. So I mean, you can actually rewrite it over R. It would just involve a little bit more complicated selection of quantifiers. So it doesn't really matter. But I mean, if you go and read one of these texts, you want to understand how this thing is proved, then you have to be ready to leave R into some, you know, these saturated models where you added a lot of non-standard real numbers and so on. Any other questions? Okay, I should say that there's also a proof by Lyon and Roland that I like, which is much more geometric. So I mean, by now there are other proofs that are geometric, but they're still not constructive. I mean, it's kind of, if you give a computer a formula and ask it, you know, I want now the negation, give me a formula for the negation, it's not clear that this can be done. Is it computable? I mean, it's not as simple as it is for a Tarski-Zeidenberg, for example. Tarski-Zeidenberg, it's quite a constructive proof. You can write it using resultants, and I mean, it's a very kind of algorithmic thing, and here it's already much more involved. Okay, so this structure is the one that's kind of normally used in most applications of o-minimality, to algebraic geometry, to arithmetic geometry, and I'll talk more about, you know, why there are applications to arithmetic geometry and why this structure is particularly useful in this application. But for today, I just want to mention that it's not obvious when I just, you know, glued up two o-minimal structures, it's not obvious that what I get as a result is going to be o-minimal. Okay, so, I mean, in fact, there is a remark, is that not always the union of o-minimal structures is o-minimal. I think that maybe the first examples are by Roland, Sands, and Shafke. They produce a very nice example of a differential equation, maybe in R, simply a vector field in R4, R5, where it has these trajectories that are not oscillating. So you can take any trajectory and throw it into your structure and it will be o-minimal. But if you throw in any two of them, it will not be o-minimal. So they're not oscillating around anything analytic, but they are oscillating around each other. Okay, so if you throw in one of them, you did not create like infinitely many oscillations. But if you throw in two of them, you do create infinitely many oscillations. So it means that there isn't some largest o-minimal structure. Right? The o-minimal structures are not all compatible with each other. So, I mean, without this result, maybe you could think that there exists some universal o-minimal structure, the biggest one, we should just be thinking about that one always. But that's not the case. So, I mean, this o-minimality is a bit more involved than that. So I just wanted to mention this. Yes.
So that's not true in theory, but is it true in practice?
Is it true in practice that there is a single one for all the interesting things?
Yeah.
At least I do not know a counterexample to this. But I mean, it hasn't always been the case. So, for instance, there is among the o-minimal structures that I didn't mention here, there are o-minimal structures where, for instance, the gamma function is defined on the positive real line. And there is an o-minimal structure where the zeta function is defined on the positive real line. And for a long time, there was no structure where both of them were defined. So it was maybe people would have conjectured that there is, but I mean, we knew a structure that contains zeta, we knew a structure that contains gamma, and we did not know whether there was a structure that contains both. In fact, quite recently, Speisiger and Roland and Selvi maybe proved that there is a structure that contains both of these. So now again, I might conjecture that, yeah, there is a single one that contains all the interesting functions, but I mean, it's not obvious, and it was, even this particular question was open for a while, whether you can put both gamma and zeta into a single structure. Yeah, so I did want to remark that there are a lot of other structures other than the ones that I mentioned here. So there's the structure of generalized power series that contains zeta. There's a structure of Gevrey functions, it contains gamma, for instance. There's the Danjoacar-Leman structure that contains Danjoacar-Leman. So there's a lot of different structures. Not all of them are known to be compatible, and kind of it's just a coincidence that we are, in arithmetic geometry, we are mostly focused on this one. And in fact, we now have some kind of new applications where you do need to go beyond RNX to prove interesting things, kind of even in number theory. So I'll talk about it in my talk in the workshop, about some joint work with Jonathan Pila and Avner Kiro, where you really need something more than RNX, even if you want actual applications in number theory. But okay, I will not have time to. I'm just doing some.
Instead of sort of examples that are actually o-minimal, that is sort of maybe more readable.
So there is a
By Roland and stuff.
There is a proof by Roland and Lyon, which is not just o-minimal, it's that it's model complete. O-minimality is a bit easier to prove than model completeness. In this case, there are several treatments using these Pfaffian methods by Chovansky, but these treatments don't quite give you that everything is an existential formula. They give you that everything is a limit of a quantifier free set. They give you a bit less, but it's still enough for o-minimality. So if you just want to understand why Rnx is o-minimal, there are kind of cheaper ways to get it. And yeah, I can give references later if somebody is interested. Okay, so this is maybe the last structure I wanted to explicitly mention. And now I want to give one theorem about o-minimal structures, which is kind of the theorem. It's the most important theorem. And it's called cell decomposition. Okay, so cell decomposition. So the theorem says that I said before that in all minimal structures, we are just making an axiom about subsets of the real line. They're just basically intervals or unions of intervals. And the magic of o-minimality is that it somehow implies that all the sets in every dimension become quite simple. And I mean, the way of expressing this is this cell decomposition theorem. So let me first tell you what is a cell. It's a very simple definition. So a cell C in R is a point or interval. Okay, I mean, you can allow semi-closed intervals if you like here. And formally, I should also allow the endpoints here to be infinite, maybe. It could be like a half infinite interval or all of R. But let me ignore these details. Okay, so this is a subset of the real line, and then you can say that the definition of o-minimality said that, okay, every definable set is a union of cells, finite union of cells. Okay, now I want to extend this to higher dimensions such that still every definable set will be a finite union of cells. Okay, so I'll say that a cell C in Rn+1, so it's going to be an inductive definition. So it's going to be something of the form xy such that x is in C prime. So C prime will be a cell in Rn. Okay, let me say C prime in Rn is a cell. And I have a set of this form. It's this and y is f of x. Or xy such that x is in C prime and y is between two functions. F of x, g of x. And these functions, fg, are continuous definable functions on C prime. Continuous defined. Okay, so basically, I mean, a cell in the real interval, it's something like this. Interval, then in R2, it's going to be, you know, I fix a cell in the base, and then I'm putting two graphs, and I'm taking everything between them. Or I could have just taken a graph. That's also an option. Here I could take a point. Here I could. Then I'm not able to draw 3 dimensions already, but okay, you get the picture. Okay, so this is what a cell is, and then the theorem is that so every definable set is a finite union even disjoint union of cells. And so this is kind of the sense in which once we've imposed this kind of structural simplicity on subsets of the real line, we get some structural simplicity for all the sets. Okay, and I mean, when you're actually using o-minimality, you're basically never using the axioms. You're always using this theorem. This is really what we were hoping to get. If our axioms did not imply this, then we would probably add some extra axioms so that they would imply this. Okay, and the way that this is often used in o-minimality is to, yeah.
So if you gave an analogous definition for closed cells, starting with, you know, a closed interval rather than an open interval, could you say that every definable set is a disjoint union of interiors of closed cells?
I would have to think what it means exactly just for the case of you know, if I take a graph, what does interior mean exactly? Because the dimension is not always full for the sets, right? So, I mean, you also have a cell which is like the graph of a function over something, and then it has empty interior. But I mean, again, if you define things properly, you could do something like what you said now. I think it doesn't make a very big difference. It's easiest to just, you know, to use the open cells, because then you can also add the endpoints as like extra cells. So it's enough to always take open intervals in the definition of a cell.
Well, I'm wondering if you can, in this description, you can ensure that the functions that you're using also have reasonable behavior at the boundary.
Okay, that's a different question. That's a very deep question. So, I mean, I didn't say much about the behavior at the boundary here. In fact, you can know, I said only that they're continuous, and I didn't say anything about the boundary. You can actually ask them to be even, let's say, CK smooth for any fixed K. For most structures, you can even take these functions to be analytic in the cell, but not on the boundary. Controlling things like derivatives around the boundary or even continuity around the boundary, it's a complicated question. And I might mention some theorem related to it in the next time. It's the Yom-Din-Gromov parameterization lemma. But I mean, controlling this behavior, the endpoints is quite complicated. So, but things can be done. I mean, for example, one of the applications of this theorem is to constructing triangulations. If you want to show that the homotopy type of your or the homology groups of a definable sets are finite, then one of the ways of doing it is to construct a triangulation. And when you try to triangulate, you want to find simplices, which basically the cells look like squares. So they kind of look like simplices already, but you do need to make sure that they glue nicely along the boundary. So just this definition that I gave you wouldn't do it, because exactly you don't know what happens at the boundary. And there is some process where you can refine the cells in such a way that they will glue nicely, at least continuously at the boundary. But I mean, it becomes a more involved question.
I'm sorry, but any structure which satisfies the cell decomposition would automatically be o-minimal. Is that right?
Yeah, definitely. So I mean, basically, if you have this even just for definable sets in R, then every subset of R should be a finite union of cells, and every cell is ever a pointer.
You could have started off with this as a definition of o-minimal.
Yeah, I mean, what I meant to say before was, I mean, somehow if our simple axiom didn't give this, then maybe we would just take this as an axiom. But in fact, there is some, let me state one corollary of this theorem, which is kind of a prototypical corollary. So it's about definable families. So when we have a definable subset of Rn plus m, we often think about this as a family. Okay, so we kind of call it a definable family. Where the fibers Ax are y in Rm, such that xy is in A. Okay, so this is, we just think about it as a family of fibers. And then I claim that a very simple consequence of this theorem is that, so a corollary is that the number of connected components of Ax is uniformly bounded independently of X. Okay, so whenever you have a definable family, you think about it as like a family of fibers, and you can ask, how many connected components does my fiber have? And I'm claiming that it's not only that every fiber has finitely many connected components, but that there's a uniform bound. And the way to prove it is to say, okay, let's start by doing a cell decomposition for this A, and then it's enough to just find this bound for every cell separately. But for every cell, the bound is 1. Okay, because just if you think about the structure of these cells, it's kind of the fiber over a point is always a cell, right? And because of the way that they are inductively constructed, if you take a cell and fix a point in the base, then you have a cell over this point. Okay, and a cell is always connected. So for cells, we have just a bound of 1 for the connected component in the fiber, and then if we have a finite union of cells, then okay, the bound for the number would be just the number of cells. Okay, and this is a very prototypical thing in o-minimality. Whenever you have some finiteness statement, you expect to get it also uniformly in families. And a lot of the statements that you make in o-minimality are always, you're trying to get some uniform finiteness, and it's kind of always as a consequence of this cell decomposition. Yes?
I'm a bit confused. I mean, if you just make the same definition but with y instead of x, you take the second parameter
Yeah,
then the proof doesn't work, right?
right. Yeah, so this cell decomposition, it's quite important the order that you do it. Of course,
It
you,
should still be true, right? Everything should be.
yeah, because you can say, well, let me flip now the direction of y and x. Then this new set is also going to be definable. It's kind of defined by the same formula, just with the variables reversed. And then let me do a cell decomposition for this new flipped set. But it would be a different cell decomposition. So, I mean, the definition of cell decomposition really depends on the order of coordinates. So, I mean, so yeah, I mean, it's still true, but it would require a different cell decomposition. It can really be geometrically quite, you know, if you look at a set that looks like this, so okay, project in this direction, it's a single cell, but if you project in this direction, it's definitely not a single cell. You'll have to like break it up into this piece, this piece, this piece, and this piece. Right? So it can really be quite different when you change the order. That's, I guess, one of the reasons why this cell decomposition, it you know, generates some internal rejection in the algebraic geometers. You know, it's in o-minimality, it's somehow similar to resolution of singularities. Especially there are certain types of cell decompositions that are called like preparation theorems, where you have you build these cells where a function looks like a monomial times a unit. So it's very similar to resolution of singularities, and it's proved sometimes using resolution of singularities, but it's extremely coordinate dependent. Right? I mean, it's kind of, you know, it depends on the order of coordinates, whereas resolution of singularities, the whole point is you're trying to make the global and not coordinate dependent. So it's a different way of viewing the world if you want to do it as a no-minimal geometer, but I mean, it has advantages because this cell decomposition is uniform in families, and the resolution of singularities is not uniform in families in a certain precise sense. So, okay, so I just wanted to say that if we assumed something like this corollary as the definition, so if we assume not just that we have a finite number of points in intervals, but that we have this finiteness uniformly over families, then actually the cell decomposition theorem would become very easy. I mean, it's not so hard to prove this cell decomposition theorem, but I mean, the hard part is getting this type of uniform finiteness in families. So we could have assumed, instead of just finiteness, we could have assumed uniform finiteness, and then this theorem would become quite easy, maybe a one-page proof. Because we only assume finiteness, then you need to work a bit more to prove this theorem. But anyway, okay, I'm out of time. I'll stop here, and next time I'll talk more about the Spiller-Wilkie theorem, what these definitions have to do with number theory, and then some kind of more advanced results in that direction. Okay.
If
Questions?
someone wants infinite time to understand why RF not be too ambitious, why RF is o-minimal. What is sort of the easiest way to convince yourself that RF is o-minimal?
So you need to either convince yourself or take as a black box the result for quantifier free sets. So that this is proved by Chovansky, and there's a very nice like geometric proof for it. But you know, you can try to read it in his book, or you can take it on faith. No, I mean he has a book, but the book does a lot. I mean it's not that hard to. So I mean you always need to understand first what happens if I don't allow any quantifiers. I'm just putting equations using exp and algebraic things, and why do I not already get infinite complexity? And then you should, I think the simplest is maybe there is a paper by Gabrielov where he shows that he shows kind of an effective proof for why you have o-minimality in this Fluffian structure without doing model completeness. So he's doing kind of a less deep result, and then the proof is quite constructive and it's effective in some sense. So I think that's maybe the path of least resistance, but maybe it depends on your, you know, for me it's the path of least resistance, but maybe for people from a different background, it's easier to read Wilkie. I mean, if you already know some model theory jargon, maybe it kind of creates a shortcut. You know, these things always depend on what your background is. But I mean, I can show you some references that might be easier for you.
So just as the heuristic, should I, when you move to these non-standard extensions of real numbers or something like this, should I think of this as something like generic points in algebraic geometry? Or is there some connection here, or is it like two totally different?
I mean, yeah, it is something like, I mean, you should think about it some generic points.
Like generic points in the sense of if you're working over generic point, you're really working over family secretly or something like this.
Yeah, so I mean, usually they are constructed using these like ultra filter products, where I mean you can think about it more or less like, yeah, it's kind of a generic point of a family in some abstract sense, but it's not quite a nice family. Like in algebraic geometry, maybe you can really pass to a function field, and you can really think that I have a family in the background. And here it would be just an ultra product over some, you know, any family. So it could be much more, it's kind of harder to understand exactly what these types means. Once you put in the order, then you have to accept that you're adding numbers that are bigger than any, you know, integer smaller than every 1 over n. There's just a lot more types. There's a lot more formulas that you can write now that you have allowed also inequality. So you have these models where you realize all the types, but they are harder to visualize than just realizing all the types in algebraic geometry. The definable sets are much more restricted. Other questions? Okay, then thank you very much.